Okay, now in the last class, we talked about determination of static forces. So we talked about static forces. And we decided, or we found out, that torques is equal to the transpose of Jacobian multiplied by forces. What that means is this: these are the forces on the end effector. Now, I want you to understand how powerful this technique is. Imagine you have this 6 degree of freedom robot arm. Imagine that you have this 6 degree of freedom robot arm. And let's just see what happens. Under its own weight, the robot falls down. So if I want to support this weight, I need to understand what are the joint torque values here I need to apply so that the robot can support its own weight. So that is a static force problem. The second thing is, imagine if you have an end effector. What you want to do is you want to make sure that the robot configuration does not change under the self weight of the end effector. So this equation that I have shown you on the board is important to understand what is the holding torque and what should be the maximum torque capacity of the servos so that the robot operation is smooth. Here is what happens, and this is a very practical robotic problem. You perform robot kinematics, you perform inverse kinematics, you find the angles, you solve the dynamics, and then you add an end effector. And what happens is you will see that your angles get off. Why do they get off? Because the inertial properties of the robot, they change. So we need to somehow account for change in the inertia properties. To start with, what you need to do is you need to cancel out the static forces before even you compensate for the inertia properties in motion. So static force analysis, this equation is super duper important. And if your robot arm is moving slowly, then you can find the Jacobian at every instance. You can find the Jacobian at every instance and then correct it. And we haven't talked about it, but once you come to robotics too, I will tell you. Many a times what happens is the robot dynamics is non-linear, but the techniques that we know very well, or the techniques that are known to solve the problem in closed form, are all linear. So somehow we have to take this non-linear dynamics and linearize it. In other words, do a Taylor series or Jacobian, something like that. So this non-linear dynamical system of equation is converted into a linear equation. What is a linear equation? One burger for $1, two burger for $2. Non-linear, for $3 you get 5 burgers. Equation became non-linear. The next thing is, many a times what happens is, even though you use these linearization tools, there is some non-linearity you cannot get rid of. So that non-linearity is going to stay, or there is some unmodeled dynamics. For an example, I can only approximate the profile. I can only find the moment of inertia approximately. I don't know the exact moment of inertia. So there is some unmodeled dynamics that also is combined with this non-linearity, and all that stuff is called as the disturbance. So what you do is you have this linear equation and then you have this disturbance. Then you design the control so that control overcomes the disturbance, cancels out the disturbance, and then controls the dynamics. And this is very powerful because this allows you to use linear techniques to solve non-linear problems. I repeat this once again. So in robotics or in aerial robotics or even complicated dynamical systems, the equations of motion are going to be nonlinear. Nonlinear equations can, there are very few nonlinear equations that you can solve in closed form. Most of the nonlinear equations you have to solve numerically. And when you start solving numerically, there is always a possibility of singularity, getting 1 divided by 0 type of error. So what we want to do is we want to minimize nonlinearity as much as we can. So the technique is you have this nonlinear equation, linearize it, and whatever garbage is left, nonlinearity, unmodeled dynamics, treat it as disturbance. Everyone understood this? And then design this controller algorithm, design this controller so that this controller overcomes this disturbance and applies enough control to control the dynamics of the system. Everyone understood this? What that means is you can use your state space techniques, then you can use your transfer function techniques, all the linear techniques that you have studied or will be studying can be used to control a nonlinear system. That is very powerful technique. And we will talk about it. I don't think I will show you how to do it in this robotics one, but in robotics 2, definitely the aerial vehicle is a nonlinear dynamical system. You have to use some tricks to control it. Okay, so we talked about the static forces. Static forces means the velocities and accelerations are zeros. But the robot arms are supposed to be moving objects. So robot arms move. So we have to find out the dynamical equations of motion. Dynamical equations of motion. Now I'm going to start with a very simple approach. The simplest approach to derive dynamical equations of motion is applying Newton's law. Remember Newton's law you studied in high school. Summation of forces is equal to mass times acceleration. Force is a vector, acceleration is a vector, and mass is scalar. Everyone understood this? There is another equivalent expression, summation of moments or torques is equal to I multiplied by the angular acceleration. T is equal to I times alpha. But there is something else that I want you to understand. There is this something called as MAD, which is basically rate of change of angular momentum. Now, this equation is the most general equation. However, if I understand correctly, most of the times we study this equation. This equation is only valid when the moment or the torque is above fixed point, above CG, and when A cross B is equal to 0. So please understand, T is equal to I alpha. This equation is not valid everywhere. This equation is valid only at few places, and those are fixed point CG and when the acceleration vector and dynamics or the distance cross product is 0. In other words, basically they are parallel to each other. So that's something like cosine theta is equal to actually when they are perpendicular to each other. Yeah, when they are perpendicular to each other. So in that case, that happens. So what I want to do is, I want to take a very simple example. So you have this spring, you have this mass, and what I'm going to do is I'm going to derive the differential equations of motion for this spring mass system. So this is called as static equilibrium position. Static equilibrium position. SEP. Now what's going to happen is I'm going to pull this mass. The spring will get stretched. Do you agree with me? If there is no damping or if there is no resistance, and if I let this mass go, what will happen is this mass will travel all the way over here and it will compress this. You agree with me? So it will cross the static equilibrium position and compress the spring all the way over here. Now let's talk about the energy stored in spring. The spring has a stiffness K. Stiffness is force divided by displacement. And if I want to find out the energy that is stored in spring, then what I do is I have force over here, I have displacement over here, and assuming the spring is linear, as you pull the spring, the force exerted by the spring increases. As you pull the spring, force exerted by the spring increases, and area under this line is the energy stored in the spring. Energy stored E is equal to 1/2 F times delta, and please understand this equation can be written as 1/2 K delta delta, which is written as 1/2 K delta square. Are you with me? So the energy stored in the spring is 1/2 K delta. This is called as the static or potential energy. Is called as the static or potential energy. Now please understand, this object has three positions. This position is B, this position is A, and this position is C. Now if there is no damping, there is no energy dissipation, do you agree with me? If I pull this mass and let it go, it's going to oscillate back and forth, back and forth, back and forth for the infinite period of time, because there is no energy dissipation. Energy can neither be created nor be destroyed. So what is happening here? At point A, this mass goes to the extreme position towards right hand side, momentarily stops and reverses its position. You agree with me? What that means, at point A, momentarily the velocity is 0. Do you agree with me? Which means the kinetic energy at point A is 0. However, potential energy, because the spring is stretched all the way to the maximum extent, potential energy is maximum. Do you agree with me? Then here, kinetic energy, again same thing, kinetic energy is 0 and potential energy is maximum. Are you with me? And at static equilibrium position, as you can see, the spring is neither stretched nor deformed, but velocity here is maximum, which means the potential energy is 0, kinetic energy is maximum. Are you with me? So what is happening? As the mass is going to part C, from C to B to A to B to C, going back and forth, there is this continuous change of kinetic energy to potential energy that is causing this mass to oscillate. Everyone understood this? So now what I want to do is, I want to draw something called as the free body diagram. So for free body diagram, as the word says, I have to free the body. So if I pull the mass towards right, you agree with me, I have a spring force Kx in this direction. If my displacement is in this direction, if my velocity in this direction, if my acceleration is this direction, I would apply the Newton's law, summation of forces is equal to mass times acceleration. Please understand, my coordinate system is, if my force is aligned with positive x-axis, it's positive. If my force is aligned with positive y-axis, it's positive. Let's see here. Can you see that my mx double dot is going towards right? So it is positive. You agree with me? And F, as you can see, the spring force is going towards left, is minus Kx. So which means the equation is mx double dot plus Kx is equal to 0. Do you agree with me? This is called as the differential equation of motion. So equation of, are you with me so far? And if I were to plot this back and forth oscillatory motion of this mass, is going to be like something like this. Are you with me? So this is the equilibrium positions, and then the mass is going to oscillate back and forth, back and forth. Now, what do I mean by solution of the differential equation? Now, I want you to pay attention. So if you look at this axis, this is my time axis, and this is my displacement axis. Do you agree with me? So the solution of differential equation is the equation of this curve. And as you can see, that's a periodic signal. What it means is you can approximate that at some sine and some cosine. How much of sine and how much of cosine is present, it depends upon the initial condition. But all in all, the solution of this differential equation is finding the equation of this curve, equation of x as function of time. Everyone understood this? This equation is linear. So you can find the solution of this equation in the closed form. But many a times these equations could be non-linear and you cannot write a closed form expression, and you have to use some type of numerical scheme to come up with an answer. Everyone understood this? So what I did, I used Newton's law to derive the equation of motion. And the next step, next logical step, is how do we solve this equation of motion? Please understand, what is m is a constant. M is the mass of the spring. A mass. K is the stiffness of the spring. X is the displacement, that is function of time. So what is the independent variable? Time is an independent variable. X double dot is acceleration. What is an independent variable? Acceleration. What is the dependent variable? Oh, sorry, what is the independent variable? Time. What is the dependent variable? Acceleration. Everyone understood this? So at the end of the day, the solution of a differential equation is the relationship, mathematical relationship between the dependent variable and independent variable. It means you can substitute the value of independent variable and get the values of dependent variable. Everyone understood this? Now, next thing which I want to talk about is there is an alternate approach for deriving this equation, and I want to talk about it. The first approach is called as energy approach or Hamiltonian approach. So please understand, this is how it starts. So total energy is potential energy plus kinetic energy. Do you agree with me? Potential energy is 1/2 k x square and kinetic energy is 1/2 m x dot square. Do you agree with me? This is called as the total energy. Since there is no damping, the total energy is remaining constant. Everyone agrees? Since there is no damping, energy is not dissipated, the total energy is remaining constant. So what I can do is, I can take the time derivative d by dt of total energy and equate it to 0. So let's find out what is the d by dt of total energy. This is going to be 1/2 k 2x x dot. Do you agree with me? So basically 2x x dot plus 1/2 m x dot square is 2 x dot x double dot is equal to 0. Do you agree with me? And then 1/2 gets cancelled, 1/2 gets cancelled, 1/2 gets cancelled, 1/2 gets cancelled, x dot, x dot. Can you see that finally you get kx mx double dot is equal to 0. Are you with me? So this is the exact same equation that we got from the Newton's law. This is the total energy, or also called as Hamilton's approach. Now the next thing is, there is a concept which is called as the Lagrangian, and we will use Lagrangian a lot in next few classes. So Lagrangian, and I want you to remember this. What is the biggest disadvantage of the Newton's law? The biggest disadvantage of Newton's law is I need to draw the free body diagram. I need to understand how the forces, internal forces, external forces are acting on this object, and then derive the equations of motion. Everyone understood this? Imagine if you have a robot that has 15 degrees of freedom. It's impractical to basically separate out those 15 bodies, write the expression for each body, and finally combine those together. So what we do is, we use something called as Lagrangian approach. The biggest advantage of Lagrangian approach is you don't have to draw the free body diagram. Lagrangian approach or Hamiltonian approach, they are based on the energy principles in physics. What is the energy principle? Energy principle is, energy can neither be created nor be destroyed, it can only change form. So if you want to derive the equation at quantum mechanics, you don't use Newton's law, you use either Hamiltonian approach or Lagrangian approach. So Lagrangian approach is an energy approach which is present and valid for the universe, even for tiny molecules and atoms. So Hamilton's approach or Lagrangian approach, which I'm gonna discuss, is super duper applicable. Now, what is it? Yeah.
So what is the use of more than 6 degrees of freedom for robots?
Oh, you can have robot. Basically, a simple example is Da Vinci robot. So Da Vinci robot is used for very fine-tuned surgical applications, right? So if you want to have a very tiny maneuvers at very microscopic scales, you will need additional degrees of freedom. So, I mean, the robots that we have studied, this is the 6 degree of freedom robot. But imagine if we were to add an end effector, or if we were to add another robot arm, then it would become more than 6 degree of freedom robot. But typically in practice, we use up to 6 degrees of freedom, but you can potentially have a robot arm that has 8 or 9 or 10 degrees of freedom, depending upon your application. Okay. Any other questions? Any questions from online students? Now, next approach which I want to talk about, and I want you to remember this approach because this is the approach that we are going to use. This is Lagrangian approach. And the advantage of Lagrangian approach is you can write a MATLAB code that will do the Lagrangian, find the differential equations of motion and integrate those differential equations of motion. So that is the beauty of the Lagrangian approach. I'm going to show you how to use the Lagrangian approach for few simple examples. But for complicated examples, as a matter of fact, for robot arms, what we will do is we'll use the MATLAB code to derive the differential equations of motion. And everything, once you know the forward kinematics, you can find out the velocities, you can find out the kinetic energies, you can find out the potential energies. Once you have the kinetic energy, once you have the potential energy, Lagrangian is nothing but kinetic energy minus potential energy. Substitute that Lagrangian in your MATLAB code, and that MATLAB code will find the Lagrangian, differentiate the Lagrangian, find the differential equation motion, and then numerically integrate that differential equation of motion and give you the solution. Everyone understood this? So what I want to discuss, super important. So this is called as the Lagrangian approach. Now Hamiltonian is total energy, where the kinetic energy is called as T and potential energy is called as V. So potential energy is V, kinetic energy is T. Lagrangian, which is called L, which is T minus V. And there is a Lagrangian equation, which is d by dt of partial L by partial x dot minus partial L by partial x is equal to 0. Now let me explain what these terms are. Lagrangian is the function of kinetic energy minus potential energy. Kinetic energy is going to have a velocity term like 1/2 mx dot square. Potential energy is going to have a term that is dependent on displacement like 1/2 kx square. So Lagrangian is going to have some terms in x dot and it's going to have some terms in x. So now what I'm going to do is I'm going to differentiate partially Lagrangian with respect to x dot. Partial L by partial x dot is the partial derivative with respect to x dot, which means x here is treated constant. Then take the derivative, but please understand this is the full derivative, not a partial derivative. Full derivative of this Lagrangian minus partial L by partial x, partial L by partial x, and equate it to 0. And this seemingly simple equation will be able to solve very many complicated problems. So what I'm going to do now is I'm going to show you how this technique is applicable. So first let's find the Lagrangian. T is the kinetic energy, 1/2 m x dot square, minus V is the potential energy, which is 1/2 k x square. Do you agree with me? Just for this part, I can actually do it directly, but just for this part, I want to do it separately. Partial L by partial x dot, which means x is equal to constant. Can you see this equation becomes 1/2 m 2 x dot. Are you with me? And minus 0. Why 0? Because I'm differentiating with respect to x dot. Everyone understood this? If you don't understand, ask me, please ask me now. Next, partial L by partial x, which means x dot is equal to constant, is equal to, so please understand, 1/2 x dot, this term becomes 0 minus 1/2 k 2x. You agree with me? Next term here, I do d by dt partial L by partial x dot. Please note this 2 gets cancelled, 2 gets cancelled. Now I have mx dot, so this term becomes mx double dot. You agree with me? And this term is as is partial L by partial x is equal to half cancels and you get minus kx. You agree with me? Now I substitute these two in the equation at top and I have mx double dot minus of minus kx is equal to 0. Thus I have mx double dot plus kx is equal to 0. Everyone understood this? So when we are going to solve the robot arm, here is what we are going to do. Whatever is the dynamics of the robot, we will solve the forward kinematics problem completely. Once we solve the forward kinematics problem completely, remember we talked about the finding out the velocities. We'll find the velocities. We will find out the total kinetic energy for the robot. We'll find the total kinetic energy for the robot. That we will treat as T. T is equal to total kinetic energy. Then we will find V, which is the total potential energy. Then we will find out the Lagrangian, which is T minus V, and then perform this calculation using MATLAB. Everyone understood this? And MATLAB would give me this expression, and we can numerically integrate this equation. Everyone understood this? So Lagrangian approach is going to be our approach of choice. And why Lagrangian approach works? Because please try to understand. There are, I don't know if you have listened to Feynman lectures on physics. So basically, 6 laws. Law of energy is a fundamental law of universe. That law governs all the moving bodies and objects in the universe. So you have to use something called as the energy methods that are valid to macroscopic level all the way to microscopic level. So energy equations are very applicable and very useful when we are deriving the motion of objects, celestial bodies, even the robot arms, even the electrons and the quantum particles. Okay, everyone understood this? So what I want to do is I want to take one more example. Now the next example is I have this pendulum, and this pendulum does not have any damping and it is displaced by angle theta. Do you agree with me? Now this pendulum is under in the gravitational load, so this will be m times g. Now what I'm going to do is this pendulum has this length L. So what we are going to do is I'm going to apply the equation T is equal to I times alpha, and T is the torque. So torque is nothing but mg multiplied by this is L sine theta. Do you agree with me? This is L sine theta. Now curl your fingers in the direction of the torque. Now I want you to identify the coordinate system. This is x, this is y, and this is z. X, y, and z. But if you were to look at the torque, can you see if you curl your fingers in the direction of the torque, my thumb is going towards the negative z-axis. It means that torque is negative. Are you with me? Curl your fingers in the direction of torque. mg multiplied by L sine theta. Can you see that this torque is going in this direction? Curl your fingers. Thumb is pointing towards the board, which means that torque is negative. Now this theta, which means this theta is in positive direction. This is again theta dot, theta double dot. They are in these. If you look at, so what you have is m times g times L sine theta is negative plus, sorry, is equal to I theta double dot. So curl your fingers in the direction of theta. Theta is going towards counterclockwise. Theta dot is going towards counterclockwise. Theta double dot is going towards counterclockwise. It means I theta double dot is positive. But torque mg, curl your fingers in the direction of the torque. Your thumb is going inside the board. So this mg L sine theta is negative. Everyone understands this? Now what is I? I is mass moment of inertia. What that means is it is given as, or it is defined as, mass multiplied by the radius of gyration square. What do I mean by gyration? Gyration means moving. Radius of gyration means the radius at which the mass is moving. Can you see? This is the point of pivot. This is the fixed point. The radius of gyration is L. So I is given as mass times radius of gyration square. So m L square. Are you with me? So I'm going to substitute minus mg L sine theta is equal to m L square theta double dot. If I cancel out this equation, L gets cancelled, and what m gets cancelled, and what do I get? I get theta double dot plus g over L sine theta is equal to 0. Do you agree with me? Now my question to you is sine theta linear or non-linear? If you look at the sine function is something like this. So clearly the sine function is not linear. But as you can see, in this small teeny tiny region, you can approximate this sine function as a straight line. So which means this can be linearized in the vicinity of a fixed point. Are you with me? So you can't do linearization at an arbitrary point. Linearization has to be with respect to something, around something. You can't do a global linearization. You can only do a local linearization. What it means is you can linearize near 0. Now, so what we do is, we say for small values of theta, for theta values of small, sine theta is equal to theta. Now I want to ask you this, probably you have seen this approximation. Sine theta is equal to theta for small values. What does it mean actually? Now, this is what it means. If your theta value is less than 17 degrees, if your theta value is less than 17 degrees, if you find sine of 17 degrees, that value will be equal to the radian 17 degrees, which means 17 divided by 180 multiplied by pi would be equal to sine 17. So remember this. So when is small angle approximation valid? As long as your thetas are less than 17 degrees, you don't go all the way to 17 degrees, up to 15 degrees, your theta's linearization is valid. So what does this mean? It means sine, and you can do this in calculator. 17 degrees is equal to 17 divided by 180 multiplied by pi. Are you with me? So this is when the linearization is valid. Everyone understood this? Any questions here? Now I can derive the exact same equation using the Lagrangian approach, or I can use the exact same equation using the Hamiltonian approach. But I want to tell you something. Have you seen those grandfather clocks where they have a pendulum? If you look at the pendulum, that pendulum is oscillating very in a limited range. You actually have physical stops from preventing that pendulum to go beyond 17 degrees. Why is that? Because if your pendulum oscillation goes beyond 17 degrees, then the time is not the linear function. The equation becomes non-linear, and the clock, the grandfather clock, will no longer track the time correctly. So what needs to happen is, if you look at the grandfather clock, what you have is you have the grandfather clock oscillations between 17 degrees. Yeah.
So this is like 17 degrees, this is like the median.
So the median is 17 degrees. Yeah. So typically, usually they go all the way up to 15. So you see, it's very small, teeny tiny. And then, and there are actual physical stops, either nails or stops, that will prevent that pendulum to go outside that bound. But for some reason, if the pendulum goes outside the bound, you will see either the clock will run fast or the clock will run slow, because time is no longer can be expressed as a linear function. Everyone understood this? So I didn't clarify this. So what happens is, if the pendulum oscillations go beyond 17 degrees, the period is function of the pendulum dynamics. The period, the amount of time it takes to complete one oscillation is not constant. That's what happens. Okay. Now what I'm going to do is, I'm going to derive this equation really quickly using the Hamiltonian approach, which is the total energy, kinetic energy plus potential energy. Kinetic energy is 1/2 I times theta dot square, and potential energy is plus m times g L cosine theta. Then what you need to do is, you need to take the derivative. So I need to write total energy. Equal to 0. If you take the derivative, 1/2 I q theta dot theta double dot plus m gl cosine theta. If you take the derivative, it's going to become minus sine theta Actually, and please understand this potential energy, since we are going below datum, is negative. So if this pendulum would have been above the datum, this is my datum, the potential energy would have been positive. This, since this pendulum is below datum, this height is L cosine theta. Since that pendulum is below datum, the potential energy is negative. Sine theta, and then you are going to have theta dot, and please understand cosine theta is minus, derivative of cosine theta is minus sine theta, so this becomes positive. And then what you do is you cancel theta dot, and you get an equation I theta double dot plus mgl sine theta is equal to 0. Are you with me? Everyone understood this? The last part that is remaining is deriving the exact same equation using the Lagrangian approach. And let me tell you, this would probably be the only time that I'm going to derive these equations by hand. From next class onwards, here is what we are going to do. We are going to use the forward kinematics, and our job from the forward kinematics is to find out the kinetic energy and potential energy. Once I have an expression for kinetic energy, once I have an expression for potential energy, I would just use the MATLAB script, and the MATLAB script will do everything. Everyone understood this? So I don't expect to perform the calculations by hand, because as soon as we go beyond 2 or 3 degrees of freedom, the calculations become tedious. So I'm gonna write Lagrangian T minus V. T is 1/2 I theta dot square minus V is, as you can see, M G L cosine theta is equal to L. Now I'm going to use the Lagrangian equation partial. So let me write the Lagrangian equation. Partial L by partial x dot d by dt minus partial L by partial x is equal to 0. Okay, I will try to do the whole thing in one shot. So if you look at this expression, my Lagrangian is going to be 1/2 I theta dot square plus M L cosine theta. So partial L by partial x, which is partial L by partial theta dot, is going to be 1/2 2 theta dot this needs to have d by dt minus mgl cosine theta. Derivative of this is going to be mgl cosine theta, derivative becomes sine theta, and with a negative sign. Do you agree with me? This will become 0. So I need to take the derivative. Oh, I forgot I here. So this will become I theta double dot plus mgl sine theta is equal to 0. And this is the exact same equation that we have. Everyone understood this? Now, for my own satisfaction, I just want to touch upon what is the meaning of solution of differential equation. So I have this differential equation. The solution of the differential equation is finding out this function x of t, and this will be some function of t, could be sine t, cosine t, could be t plus t square plus t cube, whatever it is. At the end, what should happen when I take the second derivative of this equation and substitute over here? When I substitute the second derivative of the expression over here, and when I substitute x is equal to over here, the right hand side should be equal to 0. Everyone understood this? That is the meaning of the solution of differential equation. How many of you have taken differential equations course in the past? Oh, come on, just one. Everyone, you didn't take differential equation. Oh yeah, but you took it, right? What do you remember from differential equation? I'm gonna teach you entire differential equation course in 2 minutes. So please pay attention. Wakey, 2 minutes. The only thing that you need to remember from that entire differential equation course is whenever you have a linear differential equation with constant coefficients, that's the only equation we can find the closed form equations easily. So you have to assume x of t is equal to something like a e to the lambda t. Okay. And if I have x of t is equal to e to the lambda t, why I use this equation? If you were in my linear algebra class, remember we solved an expression something like x dot is equal to ax. We found out the derivative and then find out x of t is equal to some constant a e to the at. You agree with me? So the only thing I want you to remember from your differential equation class is this. Can you remember this? Now, once you get a linear equation, what you do is, note here there is m, there is x double dot, there is 0, a plus kx. So I'm gonna do x dot of t. It's an exponential function. So do you agree with me? This becomes a lambda e to the lambda t, x double dot of t is equal to a lambda square e to the lambda t. Do you agree with me? Now I'm gonna substitute this guy in here. I'm gonna substitute this guy in here. And can you see the equation that I got is m a lambda square e to the lambda t plus k, what is x, a e to the lambda t is equal to 0. Everyone okay with me? As long as my left hand side is equal to my right hand side, I have the solution of differential equation. Everyone understood this? So now what I'm going to do is, check this out. This is where the magic happens. A cancels out. Do you agree with me? Lambda t cancels out. Do you agree with me? And the only thing I'm left with is m lambda square plus k is equal to 0. Do you agree with me? And lambda can be found out as lambda is equal to plus minus square root of minus k by n. You agree with me? Which means this is going to be plus minus. Remember, square root of minus 1 is I. So square root of k minus m, square root of minus 1 is going to be plus minus square root of k by m I. Are you with me? Since there are two lambdas, my complete solution x of t is going to be A1 e to the plus square root of k by m I t. Remember, this is my lambda 1 plus B1 e to the minus square root of k by m I t. You agree with me? Initial differential equation has how many derivatives? 2. So to find the solution, how many times do I have to integrate? 2. It means how many constant of integration am I gonna get? 2. And these are your constants of integration, A and B. So these are your constants of integration or initial conditions. That's it. That is the only thing that I want you to remember from your differential equations course, and you will be fine for the rest of your life, as long as you don't do PhD. Any questions from my online students, in-person students?